Hi everyone, welcome back to Project 2845. I know it's been a long time since we last posted, but we've got some exciting news. We finally have our transformers in. So here's a pair of the power transformers for each chassis, each monoblock, and here are the outputs. Um, Might be hard to tell, or maybe not, but these are ginormous transformers. Here's a 845 in a socket. You can see these transformers are huge compared to an 845 tube. And that's not bragging, really. They have to be this big just because of the power levels. But I wanted to take this opportunity to talk a minute about transformers in general. We often get a lot of questions, especially on power transformers, why we don't use toroids. There's a pretty good reason for this. Yes, toroidal transformers typically exhibit lower radiated noise. And what that means is there's less magnetic field energy, around the perimeter of the transformer on a toroid, just based on its geometry and the fact that the entire core has wire wrapped around it in a donut shape. And the fact that you wrap wire all the way around it helps shield the core itself. So they definitely have an advantage there. However, they have some really big drawbacks, which are or include that the core has no effective gapping. And what I mean by that is in an EI transformer, you see here all these really thin laminations that get stacked up. There's effectively little tiny gaps that get set up in the core that give a transformer tolerance for handling any DC that may flow through the transformer. Now, that might sound crazy, you say DC flowing through a power transformer. And what I mean by DC is any imbalance in the AC line that comes into a transformer by nature will therefore have some amount of DC component. So if the sine wave flowing into this transformer is not perfectly symmetric on each half, then therefore you've got a net DC offset that will have to flow through the core. Toroids hate that because they essentially will go immediately into saturation with any amount of DC offset, or therefore power line noise or anything that imbalances the perfect sinusoid of your incoming wall power will saturate a toroid. The natural gap that you have created in an EI gives a ton of tolerance for actually very poor power quality. And what this means is the outcoming power is always very representative of the incoming power. In a toroidal transformer, if the core starts saturating, you get all these nasty harmonics due to the nonlinear of the core starting to saturate. That you start squaring off that sine wave. You start spewing all sorts of harmonics on the output lines electrically. So although they can have good magnetic shielding, toroids can, they can create all sorts of noise and nasty hash on the output taps of the transformer if there's any noise on the incoming AC power. And noise on incoming AC power is extremely common. Any appliance or motor drive circuit, like your AC compressor at home for your air conditioning unit, or anything like that, can cause a lot of noise on the mains power in a house or building. And so the toroids are really intolerant of that and will basically spoil the power quality of the amplifier. And this brings up a really good point as to why we see power conditioners now showing up. I say now, power conditioners have been around a long time, but if you look at how, they've come about more recently as more toroidal transformers get used in the end equipment. And, there's a reason for this, which is the toroidal transformers can't handle, any noise on the power line. And therefore, they actually will benefit from having a power conditioner. And so you're buying this really nice, expensive piece of equipment potentially, and it's spoiled by just plugging it into the wall. And now they're forcing you essentially to buy a really expensive power conditioner. And power conditioners are a whole nother topic. They're not all created equal. Some are total gimmicks, and some really do act as good quality filters for the power. But kind of long story short, the point is that these EI core power transformers are tolerant of poor mains quality and won't spew a whole bunch of garbage on their output taps. And therefore, your equipment will sound really good wherever you plug it into. And in fact, with EI core transformers, you don't need a power conditioner to get the best sound out of them. Now, jumping back a little bit to what I said about stray fields, that's easily solvable with an EI transformer by operating them with a slightly larger core, like we do here. With the larger core, the amount of magnetic flux circulating through the core goes down, and therefore the amount of flux or magnetic field that they radiate outward from the transformer also goes down. And so this combined with proper placement completely negates a lot of the benefits of a toroidal transformer. You don't need them if you operate, an EI at a lower flux density. And that's desirable for a whole bunch of reasons. It reduces the required input current to the transformer when it's unloaded. So just to exercise the core, not even pulling a load from it, the core energy will go way down with a larger core because you'll have lower flux density. And then their temperature is also a lot lower. So having a larger core is always beneficial anyway, and we kind of don't really need the benefits of a toroid if you're building a good quality EI transformer for audio. The other way that flux problem is solved is you just keep these away with good chassis design and good wiring. These don't go anywhere near your high-end or high-gain front-end signal tubes. You're fine. And in fact, all of our products, including our Cascode 1 phonopreamp, which has 100 dB of gain nearly at 60 hertz, right where these are operating at. That is one of the quietest phonopreamps on the market, and it doesn't even use negative feedback to improve the noise performance. So it's a completely open loop amplifier, meaning whatever noise gets coupled in the circuit is there to stay. And that phonopreamp is better than most in terms of noise than pretty much anybody else is on the market that are using gobs of feedback to correct for other issues like poor circuit design and potentially poor power quality using a toroid. So something to keep in mind. The output transformers here I'm really impressed with. So we're driving again a pair of 845s, and the 845s will effectively be driving the transformer as their load, and then obviously your speakers connected to the secondary of these transformers. These have really good performance. I'm extremely pleased. We were able to estimate and predict their performance up to a couple, orders of complexity in terms of like their parasitics. So we were able to accurately estimate the capacitance of each winding, and then the capacitance between the windings in the core, and then the capacitance between like the primary and secondary. All of those were accounted for up front in our design and estimated. And I'm really pleased because our estimates match exactly what we got. So these transformers have about 60 henries of inductance, primary inductance, which gives a basically minus about half a dB down at 20 hertz. So at your low end, you're very flat. And at the high end, these do about minus 3 dB at about 30 kilohertz, which may not sound crazy impressive, but for a massive, like absolutely massive transformer with lots of management of the parasitic winding capacitances and leakage inductance with a really high impedance ratio required for an 845, that's incredibly impressive. I think that's on par with a lot of much smaller transformers where getting high bandwidth is much easier. One of the things to note about testing output transformers is a lot of manufacturers do it wrong and their data looks inflated. So what I wanted to show here real quick is kind of how we measure a single-ended, specifically output transformer. So if we draw kind of our transformer here, and we have our primary here and our secondary here. Because it's a single-ended transformer, this node here is connected to effectively our power supply. I'm kind of drawing this inverse, but we've got a power supply here, And then we've got our vacuum tube going out there to drive it. And then, of course, on the secondary, we've got our speaker load here. Now, typically, the bottom of the speaker, which is the common tap, is grounded. One of the things that's often missed when measuring these transformers, if you've got like quality measuring equipment, is you need to measure these with the primary and secondary connected together. And in fact, what I've shown in this diagram is exactly that. Through the power supply, which is providing the power to the plate of our output tube, the power supply from an AC perspective is grounded. So a good power supply with all of the decoupling capacitance that you normally have, the capacitors effectively make the power supply grounded at AC. So these two nodes in the actual amplifier are effectively connected together. That is incredibly important to capture when you're testing a transformer because you completely change the way the capacitance builds between the primary and secondary. So as I've drawn it here, with this wire in place, effectively, there's no voltage differential between the low side of the secondary and the high supply side, because it's AC grounded, the supply side of the primary. Those are at the same effective AC voltage. The DC voltage is obviously very different. This is the highest DC voltage in the transformer because we're sitting at the supply, or the highest static at least. But the AC voltage swing is 0 between these nodes. Therefore, the capacitance between these two windings is 0. So what you end up having in these transformers is a distributed capacitor that, builds across the windings as you work your way up. And so the capacitance, effectively between the primary and secondary, as I've drawn it here, is sort of triangular in shape. You have very little or 0 capacitance down here, and then as you go up, the capacitance between the primary and secondary kind of grow. It's a pretty bad drawing, and I apologize for the poor camera work here, but I hope this gets the point across. I see a lot of manufacturers testing transformers where they don't do this. And if you aren't effectively connecting the primary and secondary together like this when you test the transformer, you're going to get much better than results you'd actually get in the amplifier because you're not effectively you're not coupling both sides together and driving the capacitance that actually exists between the primary and secondary. So that's something I see all the time that frustrates me and makes it really hard to compare, one manufacturer's, transformer specs to another. So with these, obviously we test in that way. So red being the B plus or our high voltage, our 1.25 kV for our 845 plates effectively. When I test, this red gets attached to the black secondary here. Those get shorted together, and then you can run all your testing. So once you do that, then you'll get the real performance. The other thing to note with this transformer that I'm really pleased with is it's a really high impedance ratio because the 845s, as you may know, like to see, as single tubes can see up to 16 kiloohms of impedance, or wants to see 16 kiloohms of impedance to get maximum power. So the impedance of the transformer is really high. And as those winding ratios get really high to get the impedance between, say, 8 ohms and now 16 kiloohms on the primary to load the vacuum tube, things just get really, really difficult. And so the number of turns goes up. As I mentioned, all the parasitics go up. So what's impressive with this transformer is it's got great bandwidth, but also it's got really low winding resistance. So this primary is only 140 ohms, which for this impedance and this size of transformer is really good. And then similarly, the secondary impedance is extremely low. So I think the 8 ohm tap is 0.1 ohms or 100 milliohms between the black and the yellow 8 ohm tap. That's important because it's often neglected, but the winding impedance of this transformer adds directly to the output impedance of the amplifier. There's nothing you can do about it. You've got wire wound around the core, and that makes effectively a wire wound resistor that's in series with your speaker. So no matter how you design the amp, you always have an additional output impedance factor, which is the winding ratio of the transformer. Now, 100 milliohms on a single-ended output transformer with this impedance ratio, again, is really, really good. I've seen many transformers that have 1 ohm or even 1.5 ohm, 8 ohm taps that are single-ended. So no matter what you do, the output impedance of that amp, especially an open loop amp, is going to be a minimum of 1.5 ohms. Here, again, only 100 milliohms through the transformer. So the transformer adds very little impact or degrades the damping factor very, very little. Which is good because, again, the whole exercise, I didn't say the whole exercise, one of the main reasons for using a pair of 845s is, yes, we get quite a bit more power. We're going to get, 40 to 50 watts out of a pair, but we also reduce the output impedance dramatically. So the quality of the power goes way up, and we can drive way more difficult loads and larger woofers and speakers with really good precision and really good movement of the woofer. We can control it really well as the output impedance of the amp goes down. And this amp, again, is designed to be completely open loop, although we will have a switch where you can add some feedback if you so desire. So with that, the output transformer won't spoil the really low output impedance offered by two 845s in parallel. And we expect it to be, in the mid-band, the output impedance will probably be just over an ohm, which is amazing, again, for an open loop, single-ended amplifier. 1 ohm is really, really impressive. So some other exciting stuff we've got going on. Here are the final boards. So we are just waiting now on sheet metal, which is due in a couple weeks, and we will finally have this project done. Here's the boards, and actually let me stand back. This is all the hardware, at least the power supply hardware for a pair of amps. So you can just see how much hardware there is inside of these things. This is one of the power supply sections. This is actually this top board is the DC filament supply for the preamp. And then below that, we've got right off the high voltage rectifier, we have our rectifier filter, which if you've been following along with the videos, we're using film caps right off the rectifiers, which handles the really high ripple currents that we're going to see due to the high operating voltage. So ripple current is what heats and kills capacitors. So because these are film caps, these can handle really high ripple currents without heating because their equivalent series resistance is so low compared to, say, like an electrolytic capacitor. So these take the brunt of the heavy lifting and the wear and tear relative to ripple current off the rectifier, and will last a long time. Moving down the chain from power supply is actually the board below this one you see here. This is the next filter in the chain, and now we're using really high quality electrolytic capacitors. And so these are mounted, again, this is a really high voltage product. Final voltage, as I said, to the transformer and to the plate of the 845 is going to be about 1.25 kV. So we want to make everything obviously really safe, but also really serviceable. So these electrolytic caps are not bolted to the chassis. They're actually bolted to a board, and the board gets bolted to the chassis. And the reason we do that is to get our high voltage rating, we actually need to stack these capacitors in series. So 3 capacitors in series, these 3, 1, 2, 3, make up the 1250 volt supply, and then these 2 in series make up the approximately 600 volt preamp supply. And so as soon as you start stacking these in series, the negative terminal on these upper capacitors is not at ground anymore. The negative terminal is elevated by the capacitor voltage sitting below it. So for the sake of argument, if this is running at 1500 volts and we've got 500 volts, 1000 volts, 1500 volts, the negative side of this terminal is sitting at the positive voltage of this capacitor, which would be 1000 volts. The negative terminal of this capacitor is sitting at the voltage of this one, which would be 500 volts. So I'm not sure if that makes sense to you all, but basically what that means is this negative terminal is not grounded as soon as you start stacking capacitors in series. And guess what? The metal can they make these capacitors out of is effectively tied to that negative terminal. So as soon as you put a clamp around a capacitor like this, and you clamp it and then bolt it to a chassis, you're relying on the insulation of this PVC tube that they heat shrink around the capacitor can to save your product and to save potentially the user from getting, a potentially lethal shock of really high voltage at really high current, because you've got this massive reservoir of current from these caps. So with this construction method, you've got a ton of isolation before you ever get to the chassis. Yet they're mounted on these clips, so down the road, if this amp ever needs service or these capacitors eventually, after 20 years dry up and need to be replaced, replacement is easy, but everything is safe. And I can't stress that enough. Again, with cheap Chinese 845 amplifiers, they scare me and they should scare you if you open some of them up. So that's the kind of power supply for the high voltage and then the first stage of the preamp. And then this board, which was sitting on top of that radial capacitor board, has the bias supply, the fixed bias supply for the 845s, and then the final preamp filtering. So just a huge amount of hardware to make this all work and to make it work as best as it can. And, this isn't, an exercise in trying to make something maximally complicated or overly, put a lot of hardware into it to make it look impressive. This is truly what's required to make an 845 amp sound its best. Anyone who's not doing this is skimping out somewhere. And, if they don't say that, then they're, likely lying to you. Then this is strictly for our design. These are our constant current source boards that we use for our preamp. And so if you're unfamiliar with what we're doing with these, take a look at some of the previous videos. But these are basically active loading the first or the second 6H4 preamp stage, and then an active loaded cathode follower triode strapped EL34 that will then drive the grids of our 845 tubes. So anyway, lots of hardware. This won't be a cheap product, as you can imagine, but if we're going to do it, we're going to do it right and make something that's unique to us and that nobody else is going to, be able to duplicate. All of our magnetics are proprietary. We've designed them in-house. All of our circuitry is proprietary. We've got a lot of really cool things happening in this amp. There's no reason that this thing isn't going to be absolutely killer. So hope to speak with you all soon. And when I do, we should basically have the amp built, and we'll probably be doing a run through of the full amplifier. So stay tuned, and thanks all for watching. Take care.